Thank you, Sis. So let me start. Well, I was asked to give a presentation about solar eruptive phenomena. And as you will see, I try to concentrate on maybe the main things. So it will not be a full comprehensive review of everything what you see on the sun, but I hope you will not be disappointed. So, yeah. Okay. Okay, it works with the mouse. So I will talk about eruptive solar activity. Well, of course, you know that already from the previous presentations that solar activity has a continuous influence on the solar system, including the Earth. And the solar activity phenomena take place on a number of time scales from milliseconds to thousands of years. So here I will talk about eruptive phenomena, so abrupt variations of activity taking place on very short time scale, like several minutes, but some of them are extending to several days, as you will see. So why should we actually care? Well, the point is that solar activity can be harmful to us just because we live inside the atmosphere of well, I put here a little bit bold, perhaps stellar people will not fully agree with that, but it's, well, just a question of definition. It's clear that sun is variable and the sun is magnetic. So maybe I should clarify a bit more. What do I mean when I say that we live inside the atmosphere of the sun? Well, so we have to go to the images of the solar corona. So corona is the outer layer of the solar atmosphere. So this is a picture taken during a total eclipse. Another picture which maybe you are more used to, this is taken in the extreme ultraviolet. And to give you a comparison, this is the simultaneous, nearly simultaneous picture of the photosphere of the visible surface of the sun imaged in visible light or white light. So we can see that where there are sunspots, there are active regions in the corona. But well, I guess all this you have heard in the previous presentations. Another way to see the corona is to use a coronagraph. So instead of the moon, we place an occulting disk which covers, so the solar disk is here, and this is the occulting disk, and we see the same corona. And well, here is a combination of an eclipse image with a coronagraph image. So why I'm showing all this is to stress two things. So first, the solar corona is in a permanent expansion. The expansion speed is above the sound speed of the ambient medium, so it's not just a slow evaporation as it was thought in the early days of the solar terrestrial research. It's really a supersonic expansion of the corona, and it expands throughout the whole heliosphere, throughout the whole solar system. So the Earth is actually immersed in this flow of solar wind, which expands from the corona outside to more than 100 astronomical units. And well, okay, we are inside, but so what? Why it matters? Well, we had in 60s and 70s a number of crews flying to the moon, and well, we hope at some point go to Mars in the future years. And here I just put pictures from the two of these flights. So one was Apollo 16 in April 1972, and the other was Apollo 17. I think that one was the last. So that was in December 1972. And in between the two flights happened something which now we know was a solar superflare. So it was a very powerful solar eruption, which could have had bad consequences for the astronaut crews, which were, had they been traveling during the time shortly after the flare. So that's my kind of statement that now I will go to the details, and I will come back to this story and to explain exactly what could have happened. So let me show you first an introductory movie. Okay, find my mouse. All right. So this is the sun. So this is two coronagraphs on board Soho, which are looking in. And we will focus on this active region. Now it's in the corona. And these are the X-rays produced by solar flares. So we see also them produced in the extreme ultraviolet. And we are going out. We see coronal mass ejection. And in the end, all these what we can call snow. So these are the solar energetic particles. So this movie gives you a short overview. And now, step by step, I will explain what it is all about. So there are 3 solar eruptive phenomena that can be geoeffective to have a real effect on the Earth on short time scale. So first is solar flares. So they are electromagnetic radiation perturbs the ionosphere of the Earth. Second is coronal mass ejections. Their magnetic field can drive geomagnetic storms and which produce auroras, which is a very spectacular manifestation. And the final thing is solar energetic particles, mostly protons and electrons, which can be generated by both flares and coronal mass ejections, which produce radiation storms. So let's first do a little bit of phenomenology. So a solar flare, here is a solar flare observed in the passbands sensitive to different temperatures of the plasma. So, so this is essentially it's close to the photosphere, although the flare itself is probably shown in the chromospheric emission. This is the upper transition region. This is already the low corona, and while we go like this, the temperature becomes hotter and hotter. So here we are more than 10 million Kelvin, so the flare is very prominent, but we essentially can see it over the whole this temperature range. So, the standard definition of a flare is now taken, well, with the GOES data. So this is the Bastide flare of July 2000. So a flare is a local and a sudden increase of solar electromagnetic emission, which can be observed in different spectral domains. So when I say local, I mean that it's localized to a place, well, within one sunspot group. And when I say sudden, this is on time scale of minutes. So we see here that these are 3 days, and this is the X-ray emission recorded by GOES. So let's look at the red curve. So we see that during minutes, so this is 1 day, so during minutes, the solar X-ray emission increases by 2 orders of magnitude and then decreases. So this is a solar flare. So you can enjoy, I will show you a nice movie of a series of solar flares which were observed. So this is Soho observations from, I believe, October, November 2003, and there was a number of very big active regions which were producing spectacular solar eruptions. So we have seen already one here. Now there was one more here. So this is, let's say, half of rotation. So this active region will go from the east limb of the sun towards the west limb of the sun. So this is approximately 14 days. And during this time, you can see, in principle, you can see not only those flares. You see that in principle, the sun is dynamic all over. So here, in what we call quiet sun, you see that the brightness, the intensity of radiation is not constant. So there are, and now you see something very interesting. So suddenly emerged a new active region, very, very bright, and which emerged very, very rapidly, developed magnetic connections to the main active region here. So this was one of the biggest flares. I think this was what is colloquially called a snowstorm, but well, it's essentially the energetic protons hitting the detector of the telescope. And we see that this active region continues more and more flaring, and well, it's approaching the limb now. We see that although this one emerged very, very quickly, it did not produce anything too big. It's still this one which is producing all these flares, and now it will come to the limb. Well, so there was one more, and again it was accompanied by the energetic protons. Well, okay, no, I was wrong. This one also produced something finally. And now watch the strongest flare observed since quite some time. That was it. It was on the limb, so the GOES detector was saturated, so it's, well, it's actually not so clear what is the intensity of this flare. So, well, maybe just to give a bit of a comparison about the energy and power of a solar eruption. So, well, if one just takes the typical or, well, minimal maximal flare energies, you see that, well, it's very big in comparison with the world's production of energy. Well, even volcanic eruptions, well, one would need 10 million of them to have a comparable energy to a big solar flare. And also what is important is power, is that this energy is released during a rather short amount of time. So the total power of the world, well, we would need 500 million of them to have a power comparable to a solar flare. So, well, essentially the solar eruptions are the most energetic phenomena that occur close to the Earth. So next, phenomenological description will be coronal mass ejection. So coronal mass ejection, well, it's simply an ejection of plasma observed by a coronagraph. So we see this is, let's say, one of the most classical examples of CME. So we suddenly see something appearing and propagating in the field of view of a coronagraph. So to remind you again, the solar disk is here, and this is the occulting disk of the coronagraph. So there can be a huge variety of these CMEs. So we see here that difference in morphology. This one has the halo type shape, and also the speeds can be very different between, let's say, 200 kilometers per second, slower than the solar wind, which is between, let's say, 400 and 800, and the fastest CMEs go, let's say, up to 2,500 kilometers per second, which is significantly faster than the solar wind. And well, I want to mention that in principle plasma ejections are also observed in other stars, although they may correspond to different physical mechanisms. So this is the picture of Eta Carinae. So but this is of course not a coronal mass ejection, it's another kind of outburst here. A little bit to clarify about the morphology. Well, CMEs are transparent. So what we see is the emission integrated along the line of sight. Well, it's the whole corona at this wavelength is transparent. And the apparent differences in the morphology of CMEs are often due to the projection effect. So what is shown here, these are the three nearly simultaneous images of the same CME, taken from three very different vantage points. So this is the sun, this is the Earth. The image was taken, the software image was taken from the vicinity of the Earth. And there were also the two spacecraft of the stereo mission. One is here, stereo A, and stereo B is behind this blue thing, which we could not remove. But you see there are the three lines of sight of the three coronagraphs. So from the Earth, it looks like this. From the stereo B, it looks like that. And in stereo A, it looks like a halo. So depending on the viewer, depending on the vantage point, a CME can be observed either with a limited angular extent, well, angular extent from the center of the sun to the ends of them. So here it's a little bit less than 180 degrees, and here it's full 360 degrees. This is a full halo. And looking at three images like this, one can very reliably evaluate where the CME goes to. So if we see that from here it goes towards the left, from here it goes towards the right, and here it goes along the line of sight. So it's obvious that it goes essentially straight towards stereo A, so the CME goes in this direction. So this CME was very powerful, very spectacular, but it was directed to stereo A. But of course, there are halo CMEs observed from the Earth perspective, and then this means that these CMEs go towards the Earth. So important point here is how we can distinguish if such a halo CME is going towards us or away from us. Because if I would hide this picture and this picture, I don't think anyone would be able to say if the CME is going towards us or away from us. So for this, it's important to see the CME signatures in the extreme ultraviolet. And there is a number of phenomena which can be observed. So coronal dimmings, these small patches of decreased radiation suddenly appearing after the eruption. The IT waves, the large-scale waves propagating in the corona. post-eruptive arcades, here, the loop arcades, all these little loops, erupting prominences or erupting filaments when we see them on the solar disk, and a variety of limb signatures. So here it's the limb is here, and we see that essentially there is some kind of loop opening here, which is very similar to the morphology of the coronal. So if we can see some of these phenomena together with the CME, we can for sure point the source region of the CME. So in this case, well, the source region was here. This is, by the way, for the same event. So it has both the post-eruptive arcade, coronal dimmings, and the EIT wave. So to show you a little bit better this example in motion. So this is one of the eruptions. So here it's very, very spectacular. Okay, I have to press it again. Oops, no. Yeah. So what we see here is first of all, the erupting prominence. Well, so it was first as a filament. We see this dark structure. So the filament or prominence, it's a relatively cold material. Well, relatively cold means, well, 10,000 Kelvin. And the surrounding corona is 1 million or 2. So it's relatively cold. This is why it appears dark on the background of the corona. So we will see how this filament will go up and erupt. But also we will see right here below a post-eruptive arcade, which is a sequence of magnetic reconnection. I will explain a bit later. We will also see coronal dimmings and the opening of the loops. So here is the prominence going, and you see the arcade of loops, which appears. Okay. Every time. All right. We see also the dimmings. You will see a dark patch which appears here, and the only thing we don't see here is the EIT wave, but I will show it a bit later. Yeah, so there are dimmings. This is the place where the material has been taken from and ejected upwards. This is exactly the place where the CME material comes from. So it's not just the filament which goes off, but also the dimming in this part. The brightness of the sun became lower because the material has been ejected. And just to mention maybe the opening of the loops, which you will see right here above the limb, these loops become suddenly open. This is a consequence of a magnetic instability, which I will show in a couple of minutes. So there is another one, another spectacular eruption. So here we again see, well, there is a big flare and there is a post-erupting arcade here, but also we will see that, well, it produced again, well, there is associated energetic particles all over the sun. And we also see the coronal mass ejection. It's a full halo, and this one went towards the Earth. And even with one vantage point, we can be sure about that, simply because we see on the sun, on the surface of the sun, where it came from. We also see a widespread coronal dimmings. There was also an EIT wave, but, well, it's difficult to see here. So, and of course, well, you see the spectacular CME and the solar energetic particle event. Okay, so to finish with the phenomenology, I will show a bit the EIT waves. So EIT waves were discovered by using the EIT instrument, which was, well, the development was made by an international consortium, but final manufacturing was done at the Centre Spatial de Liège in Belgium. So we can be proud that a solar phenomenon is made is named after an instrument which was made in Belgium. So these waves, let me show you a movie. Okay, you'll see from here. There are large-scale waves propagating on the surface of the sun. The sun looks a bit weird here because it's a different picture, because the previous image has been subtracted from the image to highlight the weak brightness variation. So these waves are propagating across the whole solar surface. And so now with instruments like AIA on board SDO, with which this movie was made, we can follow this propagation in a lot of detail. So again, if we see such a thing, we can be sure that the CME has happened. Okay, so let's now move to physics, because, well, enough of phenomenology, so let me now try to show you a bit of different things. So essentially, in almost in every CME model, we have a flux rope. So magnetic flux rope, this is the structure with a twisted magnetic field. So I wrote you an example, which is, okay, it doesn't maybe show you the internal structure, but I think you get the point. It's a kind of structure where the magnetic field forms a spiral, while we see that the twist of the spiral is changing with the distance from the axis of the flux rope. So at the axis, the magnetic field is essentially along the axis, but around it, well, when you go to outer parts, the field becomes more and more perpendicular to that direction. So if you want, this is an essential ingredient of a CME, regardless of whether it was formed before the eruption or during the eruption. Okay, so let's go to physics. Okay, I will not torture you. It's just, well, of course, I want to explain it to you without showing much of equations. So the physics of CMEs can be perhaps best explained by the catastrophe theories, which can be well applied to CMEs. So what is shown here, it's a flux rope. In this case, it's a pre-existing. So this is from a model of torus instability. So there is a magnetic flux rope. So here we see the twisted field line. So the electric current is flowing along the axis of the flux rope. So the flux rope is immersed in the ambient magnetic field, shown here with these purple lines. And so such a configuration can exhibit a catastrophe in two different ways. One is stability, the other way is a loss of equilibrium. So I will still show you one plot, so which perhaps should be helpful to understand, but I will go slowly so you can understand it. So when people talk about instability, often this type of picture can be shown. So let's say this is a potential, so this here is a potential well, so here it's a potential hill. So you can see it as, well, as valleys or hills, and you can put a little ball in somewhere, and you see that in principle this configuration has two equilibrium positions. So first equilibrium is here, so if you can, for example, put the ball here, it will probably roll here and stay there. So this is the position of a stable equilibrium. So which means that if we make a small deviation from this equilibrium, left or right, the ball will still roll and go down to this valley, to this well, and eventually stay there after the dissipation of the motions. But however, can also have an unstable equilibrium. So we can very carefully put a ball on top of this hill. Hopefully there will be no wind, nothing. And if you don't disturb it, it will stay there because it's in the equilibrium. However, any small perturbation of this position will lead to a catastrophic behavior that this ball will fall either here or there. So this is an instability. So in this sense, so there is the variable, the coordinate x. So the potential, well, the potential function of the potential does not change. And essentially what you are moving is you are moving your ball. So in principle, if you perturb this one strong enough, you can move it out, far out from the position of the stable equilibrium, and it will still fall. So it will be still in the, it will lose its stability position. But the other way to make a catastrophe here is to change this function. Because, so well, this function is made with a single control parameter, so this is called A, and I will show you what short movie what will happen if we do change this control parameter A. Okay, so it's visible what happens. So it starts with this, and then whatever was your equilibrium position in the beginning, the stable or unstable, the final potential function does not allow you any equilibrium. So this is what is called a loss of equilibrium. So here there is no equilibrium possible. So to maybe make an analogy with the CMEs, so one can say that the parameter x, so the one which controls the stable or unstable equilibrium, may correspond to the radius of this torus, so the distance from here to here. So essentially, if you increase for some reason the radius of this flux rope, it will eventually reach the point of unstable equilibrium, and then an instability will be produced. It will go off. And the second way is to change this function. This would mean to change the external field, or rather, this will be more a ratio of certain characteristics of the magnetic field of both the flux rope and the external field. Then we will have the loss of equilibrium in this way, and again, no equilibrium will be possible, and ejection will happen. So there is a number of instabilities. What I showed in the previous slide was a torus instability, but we can think of others. So what is called the kink instability, and the kink instability you should be able to comprehend very easily. So if we take a start, we start twisting, and more twisting. You see what happens? Oh, finally, it snaps and develops a kink. I cannot pull it in such a way to come back to the normal situation. This is analog of the kink instability, which is observed on the sun. I will not say very often, but well, you see it here. So there is this model that shows what happens with the magnetic field that develops such a kink. And of course, well, all this is not new maybe to plasma people. Well, the kink instability also seen in the fusion. Well, if we want to do the magnetic confinement of the fusion, so this toroidal tokamak-like structures will, you see, it will kink. So this structure is unstable. This is one of the reasons why fusion is still, you know, not in the state where it can be profitable. So let's now move to the cartoon of a CME, and I will here explain you. It will be obvious to you all these CME-associated phenomena which we see in EUV. So what happens is that we have this flux rope, which is surrounded by the ambient field, and due to some instability, torus instability, kink instability, whatever, these field lines start to rise, the flux rope starts to rise, and below we might have the magnetic field reconnection producing the post-eruption arcades. The whole structure will generate a CME loop, and here actually in the center of this flux rope we usually see the prominence material. It doesn't have to be always, but it often happens. So okay, so I made even a cross section here, and this is what, well, this is what some people call a standard model. So the flux rope rises up together with the prominence material, and behind it there will be the reconnection, which will produce the post-eruption loops, which can be observed in EUV or in H-alpha, in X-rays, well. And this, of course, very well corresponds to what we see in coronal mass ejections. So there is the bright front, and here inside we have the core, which is the prominence. Okay, so I removed it again. Well, essentially this is what I already said. So a little bit of attention to magnetic reconnection. So it's a couple of cartoons again and illustrating what happens here. What happens here inside. So the reconnection of magnetic field lines may lead to the conversion of the free magnetic energy. So in principle, to have all this starting, you have to have a free magnetic energy, which means that the magnetic field should be not potential. With a potential magnetic field, one cannot do anything like this. One needs a certain electric current, one needs a non-potentiality, which means that there is a free magnetic energy, which is the difference between the energy of the system and the energy of the potential magnetic field corresponding to the same boundary conditions. So here, well, it's just a movie which shows you how the reconnection happens. So without going into too much details, I can say that, well, the free magnetic energy is converted into kinetic energy of bulk plasma motion. So we have the all material in this flux rope and the surrounding corona going up. So this is the kinetic energy. This is the coronal mass ejection. It also is converted in the thermal energy of plasma because there is a heating here. So we have the increased radiation. And also very importantly, this process accelerates particles which propagate down, get thermalized, and produce another component of the flare radiation. So here there will be hard X-ray sources, and well, the chromospheric evaporation will produce the soft X-ray and UV loops right here, which will also contribute to the flare radiation. So, and until the recent time, well, there was no such a good example, which I invite you to see here in this movie. This is from SDO. This is the plasma at essentially 10 million Kelvin. So there is, well, this characteristic structure, which very well resembles what is happening here. I will show it to you once again. So very nice. So here is the erupting flux rope and the reconnection happened behind, and well, here on the post-eruption loops start to rise. Okay, so I mentioned energetic particles accelerated in the reconnection region, and that produced the X-rays. So here the process is very similar to what is happening in the X-ray tube. So in the X-ray tube, we have the cathode, which is heated and emitting the electrons, which in the electric field go to anode, and which produce what is called with the German word Bremsstrahlung, which means the emission once you break. So they are slowing down, and of course it's not only the X-rays which are produced. It's also there is a lot of heating. So well, one has to cool down this thing. So this is the real thing, and this is a scheme. So this is essentially what happens in the flare. So here we have the energetic particles, well, mostly electrons accelerated and going down, which hit the solar atmosphere and produce hard X-rays, shown here with the blue, but also the softer X-rays will be produced on the corona around the reconnection site. So, well, this is the way to generate the X-rays which we see in the GOES or in RESI. Yeah, so this is these contours of these hard X-rays. This is from the RESI mission. So what happens further on with this ejected material? Of course, what we are interested in is that when this might propagate towards the Earth. So if we have our slinky, so Antonio, so I'm ejecting it, and you can pull it all the way towards the Earth. Okay, the shape will be a little bit distorted, but essentially that's what happens. So we have this enormous magnetic flux rope in the heliosphere. So a more realistic shape is shown in this picture. So, well, a CME which would propagate and hit the Earth. So now we already have the means to see the propagation of the, let's say, I will not say we will see the helix, but we will see the propagation of the front in this movie, which is made with observations taken by the stereo mission. So I will show you the movie shortly, but first I will try to explain you what we see. So the sun is a tiny dot right here. This is the field of view of the stereo coronagraph. And then there are two fields of view of heliospheric imagers, which cover the whole distance from the sun to the Earth. So the Earth is here. So here, unfortunately, I have to get out of the PowerPoint to show you this nice movie. Just be patient. Okay. Yeah. So here we see, we see also the quiescent solar wind, which all the time goes out, and sometimes we see these nice fronts, which are. Let me show it to you once again. We see these nice CME fronts, which are propagating from the sun towards the Earth, and well, we can even see the moment. Well, okay, this is of course in projection, but this CME did hit the Earth as shown here. And let me move on. Well, I see there is not that much time left, but I still would like to show you a bit about energetic particle events. No? Wait, okay. So accompanying solar eruptions, we can see energetic particle events. So these are a very, well, sudden or sometimes less sudden increases of the particle flux. So essentially these are here the protons, which go up by orders of magnitude, 1, 2, 3, 4 orders of magnitude, and might last for several days. So a solar eruption might accelerate particles in several ways. So the first is, as I already said, there is the reconnection happening in the flare, but that one mostly accelerates the electrons towards low altitudes. There is a part which does go to the interplanetary space, but not that much. The shock wave driven by the fast CME, this is the crucial ingredient to produce the energetic particles. So a bit about the shock waves. So a shock wave in MHD, this is a sharp increase of plasma speed, magnetic field, temperature, and density. So we have the four quantities which are simultaneously jumping up. And so this is what we see on the fronts of coronal mass ejection. So we are pretty sure that here along this line, this is the shock front, the shock wave. And on the surface, this is not for the same event, but in the solar atmosphere, it often corresponds to EIP waves. Although here there is a question if it's actually shock, but well, it will be probably shocked at some point. So this here, and here I showed a little bit of more, maybe what is more familiar to you. I don't know. So if we have a shot, there is a bullet, and the shock wave is here. The first front, this is a shock wave. Of course, there are more waves, and probably there is one more shock which is produced just because of when the bullet comes out of the barrel. But well, essentially here we can say it's analogous to a CME, so a CME drives a shock wave in front of it. Of course, a classical example of a shock wave is in a nuclear explosion. So this cloud is not a shock. The shock is in front. So this white kind of, I think the water was boiling there. So this is the ground track of the blast wave, the shock wave produced by the nuclear eruption. And of course, the supernova shock. So this is a supernova remnant of supernova of year 1006. And here we can see it's a very sharp edge. So well, it's very clear that here is still the plasma is shocked. So the shock waves in the heliosphere, there was quite some discussion in the 50s and 60s before we had the good observations of the sun. So one idea was that it's a black wave similar to the nuclear explosion. Well, usually people were thinking that this explosion is a flare, which produces then a thermally driven explosion, which drives a blast wave. So here you don't have a CME. And the second idea is that it's actually a piston-driven shock. So if you have a piston, so here it's a bulldozer moving in the snow, and which can pile up material in front of him, and you do have a kind of shock here, and this is what corresponds to the CME. So there is a CME erupting here, and in front of it appears a piston-driven shock wave. So now it's pretty clear that the transient shocks in the solar system and the heliosphere are produced in this mechanism. When I say transient, because there are shocks which are linked to the quasi-stations, both because of difference of speed, but this is not the point here. If we are talking about the eruptive phenomena, this doesn't work. What works is the CME-driven shock. And this shock can accelerate particles. So a little bit of physics again. So this is the shock front. So this is the upstream, this is the downstream. Here the plasma is faster, here the plasma is slower. And in addition to this laminar flow, there is a lot of turbulence inside. You see this small scale structure and waves which are present on both sides of the shock. Here, of course, the turbulence is increased. And what happens is that particles are bouncing of all these little turbulent waves on both sides of the shock and gain energy, because here a reflection behind the shock happens with energy gain, because the upstream flow moves this way. So it can be seen in this cartoon. So this is the shock, and we have the kind of rocket which hits the ball, and if your heater moves this direction, you gain energy. And here this illustrates that it moves there, and so you a little bit lose the energy at each position. But with multiple, as you see, you gain more than what you lose. So with many of such reflections, you get particle acceleration to a very high energies. So again, well, this is the process which takes place in both on the sun and in the universe. So again, the solar and the supernova shocks are shown here. So the only difference is that this leads to the appearance of solar cosmic rays, and supernova explosion lead to the production of galactic cosmic rays. But the physics is very similar. Okay, maybe I will skip this slide and move. So now I think you can appreciate this movie much more, because I hope you do understand the more about the physics of what's happening. So again, we are zooming in on an active region at the limb, which will produce a flare. So in the UV as well as in X-rays. So red is soft X-rays, and there will be a bluish, I think. Yeah, these are the hard X-rays, post-eruption arcades. And we see a coronal mass ejection going all the way out, driving a shock which accelerates the particles which are coming to our telescope, which is, by the way, not at all intended to register energetic particles. We see them. So, and a summary of the modern paradigm of how it all happens physically. So in the old paradigm, we would have a magnetic reconnection driving a flare, which would produce heating and thermally driven material ejection. So this would be essentially the shock produced by the blast wave, and in the same time driving particle acceleration. So this has been discarded now, and since the seminal paper by Jack Gosling, well, we have a different paradigm, that what is essential is the evolution of the solar magnetic field. The quasi-stationary, very slow evolution might lead just to reconnection, then the flare would appear accelerating some particles. But this could be only an impulsive particle event. This would never last for days like it can happen in reality. Or the evolving solar magnetic field might develop towards some instability, which would lead to a coronal mass ejection, which would move up, and the reconnection behind would produce a flare with its consequences. But if the CME is very fast, well, faster than the characteristic speed in the ambient medium, it can drive interplanetary shock, which can lead to particle acceleration and intensive gradual proton events. And if the coronal mass ejection arrives to the Earth and has a suitable magnetic field configuration, it will produce a geomagnetic storm and aurora. Finally, what was the danger for the astronauts, for people who go to the moon and in the future who will go to Mars? Essentially, it's the proton event. This super flare was accompanied by a very, very high flux of highly energetic protons, which, as we now understand, are mainly produced by the shock wave driven by the CME associated with this super flare. And so, well, they would get a very high, maybe lethal dose of radiation on their way to the moon, because they would be out of the Earth's magnetosphere, which protects our planet from the same fate. And I will finish with a nice movie which shows you the same process of eruption, but in a little bit of an artistic way. Okay. So, well, it actually goes from the core of the sun. So these are, I think, supposed to be the protons in the solar core, which will, at some point you see, well, produce a nuclear reaction and emit the energy, the light, which will be propagating inside the sun. Well, first there's a radiative transfer, then in the convection, so that's this light going up towards the surface. So here you already have the convection, but I think we are still inside the sun. And in the convective zone, it's not only the energy which is transmitted, but also the magnetic field. So these are thin lines, the magnetic field lines, which are emerging now from below on the surface, producing sunspots. And, well, rise in the solar atmosphere like as coronal loops. So here we see the dynamic chromosphere, and, well, yeah, again, these very spectacular coronal loops. And also now we will soon have an eruption. Yeah. So here, so some part of material goes up, part of material falls back. So here we have a prominence. This will be another prominence eruption, I believe. Yeah. Here most of the material falls back. It's not always that the magnetic free energy is enough to eject the CME in the interplanetary space. And now look at this filament. A very spectacular eruption. This did go out, although some parts still fall back to the surface. And well, now our coronal mass ejection is going towards the Earth. And this is our pale blue dot. And the CME coming to it, but don't worry, this is very tenuous, it's not too dense, all this plasma, and we have the shield, we have the magnetic field. Here it is visualized, well, so these are the field line, of course, and now you will see the full magnetosphere, so there is a magnetopause, there are electric currents flowing in it, and this is our shield against this harmful influence of the sun. And so we have energetic particles which are streaming down the field lines and producing spectacular auroras. And a little bit more, so now they illustrate the processes in the tail of the magnetosphere, and there might be stretching and reconnection here. And again, these particles are accelerated along the field lines, and again, hitting the Earth's atmosphere and producing the auroras. I think this is the end of it. I thank you for your attention, and if you have questions, I'm glad to answer.